In the first part of the 777 engine series, the engine was left running at the idle power. The thrust of the engine from this point will be controlled by using the thrust lever. Advancing the lever from idle sends a signal to the electronic engine control. The EEC commands the hydro-mechanical unit to adjust the fuel metering valve in proportion to the thrust lever position. The HMU increases the fuel flow rate to the combustion chamber and matches the engine thrust to the lever settings. Speaking of thrust, it's not the only desired power from the jet engine. Which brings us to the main theme of this second installment: the engine outputs. The engine provides three important power for the operation of the aircraft systems. First, let's look at the electrical power. 777 has two main electrical buses that distributes power to all the other buses. The APU generator has been supplying to both the main buses. At any given time, the aircraft should have two power sources, or else the electrical load management system gives priority to the essential loads of the aircraft, and sheds power to the non-essential loads such as galley equipments and passenger entertainment systems. With the left engine now running, an integrated drive generator on the gearbox is ready to supply the electrical power. Electrical components on the aircraft are designed to work on 415 Hz frequency. During normal flight operations, the engine is used at various thrust settings, which means the RPM of the engine keeps varying. This is not an ideal situation for the generator, as the change in N2 RPM will constantly change the generator output frequency. Variable frequency supply can damage the electrical components. Therefore, the IDG is a combination of a constant speed drive and an AC generator. The constant speed drive ensures the generator is driven at a constant speed, despite the changing N2 RPM. As a result, the generator gives a steady 415 Hz output, ready to be supplied to the aircraft loads. Ensure the IDG breaker switch is on, and the IDG will automatically supply power to the left buses, and the APU generator supplies only to the right buses. The load management system, now with two sources of power, stops shedding the non-essential loads. The galley equipments and entertainment systems are now available for use. In case the IDG malfunctions due to excessive heating, a drive light illuminates on the disconnect switch. Using the switch mechanically decouples the IDG from the gearbox, and prevents further damage. Once using the disconnect switch, the IDG is not available for the remainder of the flight. On most of the aircraft this means total loss of electrical power from that engine, but not on the GE90, which has a backup generator. The backup generator does not have a constant speed drive, therefore its output frequency varies with N2 RPM, and cannot be fed directly to the electrical components. The output is first sent to a converter, which changes the variable frequency to a constant 415 Hz, and supplies it only to the essential loads of the aircraft. Next, the hydraulic power. The left engine pressurizes the left hydraulic system of the aircraft. Hydraulic fluid from the left reservoir tank is transferred to the engine-driven hydraulic pump on the gearbox. The engine hydraulic pump switch is always on for automatic operation. The pump pressurizes the fluid to 3,000 pound per square inch pressure and delivers it to the aircraft components. The left hydraulic system pressure can be used to operate the left engine thrust reversers. Left wing aileron. Left flaperon. Number 2 and 4 flight spoilers. The right aileron. Number 11 and 13 flight spoilers. The left and right elevators and the rudder. The rest of the components are powered by the center and right hydraulic systems. The last engine output, the pneumatic power. The engine bleed air is controlled by an aircraft computer called the Air Supply Cabin Pressure Controller. Before taking the engine bleed for aircraft systems, the ASCPC computer ensures there is no line pressure in the pneumatic ducts. Therefore it commands the APU bleed valve to close. APU bleed was used for starting the engine and is no longer required. The ASCPC computer controls the engine bleed with the help of two electro-pneumatic controllers. The controllers take pneumatic line pressure from the high-pressure compressor stage and use it to operate several valves of the bleed system. The bleed air from the engine is taken from the high-pressure compressor's fourth stage. The fourth stage air, also known as intermediate stage pressure, reaches the pressure-regulating valve. Just like electrical and hydraulic switches, the engine bleed switch is always kept on for automatic operation. The controller opens the valve, and the bleed air is sent to the aircraft distribution ducts. In order to meet the demands of all aircraft pneumatic loads, the distribution duct must have 40 pound per square inch gauge pressure. If the pressure of the bleed is insufficient, then the controller commands the high-pressure shut-off valve to open, and the bleed from the ninth stage of the high-pressure compressor gets added. Using the engine's high stage pressure also means a significant rise in the temperature and can damage the aircraft's distribution systems. Therefore, the controller directs the fan air valve to open. Engine bypass airflow passes through a duct that connects to the pre-cooler. The pre-cooler is an air-to-air heat exchanger that reduces the bleed air temperature. The distribution ducts transfer the engine bleed air to the air conditioning packs. Hydraulic reservoir pressurization. For opposite engine starting. Wing anti-icing. Air-driven hydraulic pump operation. Aft and bulk cargo heating. For APU starting. The APU on the 777, along with electric, also has a pneumatic starting option. The engine anti-icing system does not use the aircraft pneumatic supply, as it is self-contained within the engine. The engine anti-ice switch is kept in auto position for automatic operation. When the aircraft encounters a bad weather condition, ice formation on the leading edge of the engine inlet cowl can be fatal. To prevent this, icing is sensed by the ice detector probe. The detector informs the engine anti-ice computer of an icing condition. The computer now sends a signal to the anti-ice controller. The controller takes the pneumatic pressure from the compressor stage and uses it to open the engine anti-ice valve. The bleed air from the seventh stage of the high-pressure compressor travels to the inlet cowl of the engine. Hot air circulation to the leading edge prevents any possible ice formation. The anti-ice system continues to function as long as the detector gives icing signal, and once the bad weather subsides, the controller closes the anti-ice valve and stops the system. In the next chapter, we'll look at the GE90's performance control. Thanks for watching.